A single superflare releases more energy than 1 trillion hydrogen bombs. For most of a century, we believed our sun was too old and too gentle to produce one. Then a team at the Max Planck Institute added up 220,000 years of activity from stars nearly identical to ours, and found that a star like the Sun fires a superflare about once every 100 years. As they published that number, a monster sunspot was already turning to face the Earth. This is the story of what has been hiding inside the most familiar light in our sky, and why once a century should terrify you. There is a dark region on the face of the Sun this week, and it is pointed at us. Astronomers have catalogued it as the largest and most magnetically tangled group of sunspots on the entire solar disk, a knot of twisted magnetism roughly 100,000 kilometers across. You could line up 7 Earths inside it and still have room to spare. For days it has crackled with flares, and it has rotated, slowly, into the one position that matters most, squarely facing our planet. If you follow space weather, you have heard this kind of warning before. A big sunspot turns toward Earth, forecasters raise the odds of a flare, the aurora dips a little further south than usual, and then the sun quiets and the world moves on. That is the story we have learned to expect, but the sunspot is not the terrifying part. The terrifying part is what a study published at the end of 2024 revealed about the star this sunspot belongs to, because for as long as we have trusted our sun, we have trusted it for the wrong reason. And a team of scientists just finished counting something that should change how you look at the light coming through your window. This is the story of what our sun is actually capable of, and why the calm we have always assumed is a kind of luck we may be about to run out of. For most of the history of modern astronomy, we sorted stars into the dangerous and the dependable, and we placed our sun firmly among the dependable. The dangerous ones were young and fast. A newborn star spins quickly, tangles its magnetic field into violent knots, and hurls out flares thousands of times stronger than anything our sun produces. Those stars flicker and rage. Ours, we believed, had grown out of that phase. Our sun is about 4.5 billion years old. It turns on its axis slowly, once every 25 days or so. Its magnetic field is orderly by stellar standards, its temper mild. The comforting logic went like this. A middle-aged, slow-spinning star like ours simply does not have the magnetic violence left in it to produce a truly catastrophic flare. The worst it could manage, we thought, arrived maybe once in a few thousand years. If that. That belief was not lazy. It was built on real data. When NASA's Kepler telescope first surveyed tens of thousands of stars, an early study in 2012 found that sun-like slow rotators produce their largest flares only about once every 800 to several thousand years. Rare enough to feel abstract, rare enough to file under someday, and someday under never. The problem with someday is that it depends entirely on how carefully you counted, and it turned out we had not counted carefully at all. The difficulty with understanding our own sun is that we have only watched it closely for a few decades. A star measures its life in billions of years. Asking what our sun does once a century, from inside a human lifetime, is like trying to describe every storm a coastline has ever seen by staring at the water for a single afternoon. So a team led by the Max Planck Institute for Solar System Research in Germany did something clever. If you cannot watch one sun for thousands of years, watch thousands of suns for a few years each, and add the time together. As one of the researchers, Sami Solanki, explained, we cannot observe our own star across the centuries, but we can monitor thousands of stars very much like it, and let their combined behavior stand in for ours. They pulled the records of the Kepler mission, which had stared without blinking at one patch of sky for 4 years. From the 200,000 stars in that field, they selected 56,000 that closely matched the Sun in temperature and brightness, genuine solar twins. Then they added up all of that observation time. The total came to something staggering, the equivalent of 220,000 years of stellar activity, watched all at once. And in those synthetic centuries, they went looking for the brightest, most violent thing a star like ours can do. They went looking for superflares. A superflare is not a large version of an ordinary flare. It is a different order of event. The team defined it as a burst releasing more than 10 to the 27th joules of energy, a number so large it slips past comprehension. Put it this way instead. A single superflare carries more energy than 1 trillion hydrogen bombs, released in a matter of minutes. It makes every flare our Sun has produced in the age of telescopes look like a spark. Across their 56,000 suns, the team found 2,889 superflares, scattered across 2,500 stars. When they worked out the rate, the answer landed with quiet force. A star like our Sun produces a superflare, on average, about once every 100 years. Once a century. Not once in 10,000 years. Not a freak event reserved for younger, angrier stars. The first author, Valery Vasiliev, admitted the team was startled. They had genuinely not expected Sun-like stars to be so prone to these eruptions. The new number was 10 to 100 times more frequent than the older estimates, and the reason for the gap was almost embarrassingly simple. Earlier surveys, when they could not be sure which star in a crowded image a flare had come from, simply threw those stars out. They had been discarding the evidence. When the team instead traced each flare back to its exact source, the true rate emerged from the noise. Once every 100 years. Hold that number, because the obvious question is the one that should keep you up. When was the last time it happened to us? And the answer is not written in any telescope's log. It is written in wood. In 2012, a doctoral student at Nagoya University named Fusa Miyake was studying the rings of ancient Japanese cedar trees. Trees pull carbon from the air as they grow, and among that carbon is a rare radioactive form, carbon-14, produced when high-energy particles strike the upper atmosphere. In a normal year, the amount barely changes, but in the ring corresponding to the year 774, Miyake found something that should not have been there. A sudden spike in carbon-14, about 20 times the usual year-to-year variation. Something had flooded Earth's atmosphere with radiation in a single year, more than 1,000 years ago. The signal was not confined to Japan. It appeared in tree rings in Germany, in Russia, in North America, in New Zealand. The whole planet marked in the same year. And when scientists checked polar ice cores for beryllium-10, another particle-made isotope, they found the matching fingerprint frozen into the ice. The source was the Sun. In the year 774, our calm, dependable star had struck the Earth with a storm of particles beyond anything in the modern record. It was not alone. A second event shows up 200 years later, around 993. Others are dated to 660 before the Common Era, to 5259, to 7176. We now count roughly 5 confirmed events and 3 more suspected within the last 12,000 years. About 1 every 1,500 years. These are the Miyake events, and they are not a theory of what the Sun might do. They are a record, pressed into living wood and layered ice, of what the Sun has already done to this planet. We had the proof the whole time. It was growing in the forests. We simply had not learned to read it until now. There is one solar storm every history book agrees was severe, and its name is Carrington. On the 1st of September, 1859, an English astronomer named Richard Carrington was sketching sunspots when he saw a sudden flash of white light erupt across the sun's surface. The first solar flare anyone had ever witnessed. The eruption that followed reached Earth in about 17.5 hours, an astonishing speed that betrayed its power. What it did when it arrived reads like something out of fiction. Telegraph networks across Europe and North America failed. Sparks leapt from the equipment. Operators received shocks. In some offices, the telegraph paper caught fire. In Portland and in Boston, operators disconnected their batteries entirely and kept sending messages for hours. Powered by nothing but the current, the storm itself was pushing through the wires. The aurora, normally a polar spectacle, was seen over Cuba, over Hawaii, over the Caribbean, over Colombia. In the Colorado mountains, the sky glowed so brightly that campers rose and began making breakfast, convinced the dawn had come. For more than a century and a half, Carrington has been our benchmark for the worst the sun can do. And here is where the new study lands its heaviest blow. By its own measure of energy, the flare behind the Carrington event released only about 1/100th of a superflare. The most powerful solar storm in recorded human history was 1% of what the data now says our sun produces roughly once a century. Carrington was not the ceiling. Carrington was the floor, and it struck a world lit by candles and connected by telegraph wire, a world that could still make breakfast by the light of the sky. Ours cannot. If all of this feels safely locked in the past, consider a date that is not history at all. 14 years ago, almost to this very day, the 23rd of July, 2012, the Sun launched one of the most powerful eruptions ever measured. A coronal mass ejection, 1 billion tons of magnetized plasma, tore away from the surface at up to 3,000 kilometers per second, more than 4 times the speed of a typical eruption. It moved so fast because another blast, days earlier, had cleared the road ahead of it. That storm crossed the orbit of the Earth. It swept through the exact region of space our planet travels through, and it missed us, because at the moment it erupted, the piece of the sun that fired it happened to be pointed somewhere else. Had that same region rotated into view about 1 week earlier, it would have been aimed directly at Earth. Instead of hitting us, the storm struck a spacecraft called Stereo A, which was watching from the side and recorded the whole thing. When scientists analyzed what Stereo A had seen, they concluded the storm may have been as strong as Carrington, or stronger. Daniel Baker, the physicist who led that analysis, put the near-miss into 8 words that have never left me. If it had hit, we would still be picking up the pieces. Another researcher studying the odds estimated the chance of a Carrington-class storm striking in any given decade at about 12%, not once in 10,000 years, roughly 1 in 8 every 10 years. We did not dodge that storm through preparation or warning or defense. We dodged it because of where the sun happened to be looking. And luck is not a plan. Picture the moment it does not miss. Imagine you could stand outside on the night a superflare-class storm reaches Earth and see what is actually happening above you. You would feel nothing at first. The light from the flare arrives in about 8 minutes, the same as ordinary sunlight, and it is invisible to your eyes. A flood of X-rays washing across the dayside of the planet, silently scrambling radio signals, and the timing of the satellites we navigate by. The real blow is still coming, still crossing the emptiness between the sun and you, a wall of magnetized plasma pushing through space over the hours that follow. Then the sky begins to move. The aurora, which you have only ever seen in photographs from the far north, blooms overhead in curtains of red and green, and it doesn't stay near the pole. It slides down over cities that have never witnessed it, over rooftops and streetlights, brighter than the moon, rippling from horizon to horizon. It would be, without exaggeration, one of the most beautiful things a human being has ever seen. People would come outside to watch. They would raise their phones to a sky on fire. And underneath that beauty, in the wires beneath your feet and the transformers humming at the edge of town, something else would already be going wrong. Because the same magnetic force painting the sky is reaching down into every long conductor on the continent, and it does not care that we have built our entire civilization out of them. Here is the mechanism, and it is the quiet heart of the danger. When a storm's magnetic field sweeps across the planet and shifts, it induces electric currents in anything long and conductive. Power lines strung across whole countries. Pipelines running for thousands of kilometers. These are called geomagnetically induced currents, and they are slow, creeping, direct currents flowing through a grid designed for something else entirely. They push into the huge transformers at the joints of the power network and force their iron cores into overload, where they overheat, distort, and can burn out for good. This is not speculation. On the 13th of March, 1989, a geomagnetic storm far weaker than Carrington reached Canada, and the entire Hydro-Quebec power grid collapsed in about 90 seconds. 6 million people lost power for 9 hours in the subarctic cold. And that was a minor storm by the standards of what the sun can do, striking one regional grid. Now scale it up. The transformers most at risk are not shelf items. They are custom-built giants, weighing hundreds of tons, costing millions of dollars each, with waiting lists of 1 to 2 years, and many of them are made overseas. Destroy a few hundred of them in a single afternoon, and you cannot simply order replacements. A United States National Academy's assessment estimated that an extreme storm could leave more than 100 million people without power, damage more than 350 of these transformers, and cost between $1 and $2 trillion in the first year alone, with full recovery taking 4 to 10 years. An analysis by Lloyd's of London reached figures in the same terrifying range, and every one of those numbers describes a Carrington-class event, 1% of a superflare. This is what the floor costs us. We have never once calculated what the ceiling would do, because until this study, we did not believe the ceiling applied to our sun at all. It would be dishonest to tell you a superflare is coming tonight, or this year, or in your lifetime for certain. The scientists themselves are careful here, and so should we be. The study establishes how often stars like ours produce the brilliant flash of a superflare, but not whether every one of those flashes launches a storm aimed at Earth, and not exactly how the flares in the sky connect to the particle events buried in the tree rings. Those questions are still open, and the researchers say so plainly. But look at what has not stayed open. The frequency we trusted was wrong, by a factor of 10 to 100. The historical record already shows the sun striking this planet with storms beyond anything we have instruments to measure. Our single modern benchmark was 1/100th of the real maximum, and even that would break the world we have built. And 14 years ago, we crossed the path of one of these storms and survived only because the sun was facing the wrong way. Put those facts together, and the picture is not a doomsday clock ticking toward a fixed hour. It is something quieter and harder to dismiss. The event we had comfortably placed once in 10,000 years belongs, on the best evidence we now have, to a far shorter clock, one measured in centuries, on a star that has already hit us before, watched over by a civilization wired end to end and utterly dependent on the wire. We told ourselves our star was too old and too steady to end anything. We looked up at that even, reliable light and read it as a promise. The study out of Germany, the rings in the cedar, the ice at the poles, and the near miss of 2012 are all saying the same thing in different languages. The promise was never made. We only assumed it. The sunspot facing us this week will very likely rotate away without incident, the way almost all of them do. That is not the point. The point is the star behind it. A star we now know is capable, roughly once a century, of an eruption that would rank among the most violent events in the recorded history of our planet, and that has already delivered several. The calm we have always felt looking at the sun was never the sun being gentle. It was the sun between breaths. The most unsettling discoveries are rarely about something new appearing in the sky. They are about learning, too late to unlearn it, what was always there. Our sun has not changed. Only our understanding of it has. And the next time you feel that warmth on your face and mistake it for safety, remember what more than 50,000 stars just taught us about the one we depend on. Thanks for watching, and I'll see you in the next one.